is very similar to something that you did in Algebra 2. A few things may be new or maybe a different way of phrasing. So I'm going to go to the first slide, and I just want you to write everything down. I'll give you a couple minutes to do that, and then I'll talk about what it is. So as I'm talking, you can jot down in your own words if you want. Okay, so right now, everybody just write. Okay, so let's go ahead and kind of put in our own words what these two theorems are saying. The first one is the fundamental theorem of algebra, and it's nothing really groundbreaking. Okay? First of all, it's going to start off. If f of x is a polynomial of degree n, so the highest exponent is n, where n is greater than 0. So the first degree we're talking about would be 1, which is linear, then 2, which is quadratic, 3 is cubic, so on and so on. So we're basically excluding from that the constant function, if you'll remember the constant function. Then f, the function, has at least one 0 in the complex number system. So we're saying the linear function, the quadratic, the cubic, the quartic, there has to be at least one 0 that exists in the complex number system. Remember, the complex number system are both real answers and imaginary answers. Okay, so it could be both or either. The linear factorization theorem, and the word factorization showed up on your quiz yesterday. Some people were kind of saying in the reflection, I didn't know what that meant, right? What word is in there? Factor. Okay, so it's really just like the linear factors. It's just another way to talk about factors. So the groups of parentheses, x minus k, those types of things. If f of x is a polynomial of degree n, where n is greater than 0. So we're talking about the same things that we're talking about in the fundamental theorem of algebra. We're just building off of that statement. Then f of x has n zeros and n linear factors. N represented what in the polynomial? The degree. Now, we kind of already covered that a little bit in the explorations that we did for graphing in section 2.2. But what we saw in the graphs was the maximum number of zeros was n, equal to the degree, but it didn't always have all the zeros on the graph, like x-intercepts. Okay. Every function polynomial that has degree n has that many zeros. Some of them could be imaginary, and we kind of also talked about that. We knew that from Algebra 2. So some of them could be imaginary, some of them could be real. And then for n linear factors, if I ask you to write out the linear factorization for a polynomial and it's cubic, then you have to have 3 linear factors. If it's 5th degree, then you have to have 5 linear factors. So that's a way for you to check, do I have all the factors? Next up, we're going to talk about complex zeros. So I'll give you a minute to write this down. So this is a pretty simple statement. Sometimes it's referred to as the complex conjugate theorem. And it just says, if you have some zero that is a plus bi, then a minus bi, its complex conjugate, must also be a 0. They always come in pairs of their conjugates. And if you think back to like how you solve by completing the square, or when you do quadratic formula, you know, that has that plus or minus the square root of. So if you do the square root of a negative number, you're going to get plus or minus some I value. So it makes sense when we think about how we solve that they always come in pairs. That's also true for the irrational zeros. So like if 2 plus the square root of 3 is a 0, 2 minus the square root of 3 also has to be a 0, because the plus or minus comes from the square root. Okay, so we're going to just do write the linear factorization of a polynomial that has the given zeros. 0 and 2 plus I. Linear factorization is just like factors like x minus k. So where would you start to write the linear factorization? What would be your first factor? X. Yeah, I'd start with x. Now, some people might write that first 0 as x minus 0. That's okay, but would you all agree if we take nothing away from x, it is still x? So anytime I see 0 as a solution, I'm going to write that as a factor of x. I don't want that minus 0. That's just more stuff to make it look more complicated. What's our next factor? X minus, and then if you want to say 2 plus I, you're really subtracting all of 2 plus I, right? So technically, that would be in a group of parentheses. Or you could think about that as, I'm really subtracting that whole 0, so both pieces are going to change signs, right? So that factor could also look like minus 2 minus I. And you can take your pick which way you'd want to think about that. If you want to have the extra parentheses there. Is that it for your linear factorization? Okay, you have to think, even if I only give you one imaginary 0, think about complex zeros. They always come in pairs. 2 minus I is also a 0. So if you only get one imaginary, you put in the other. You know it has to be there. And so we would add another factor, could write it as x minus the whole 0, 2 minus I, or you might distribute that, it'll be x minus 2 plus I. Now, this is the linear factorization. Notice that all my factors, when I look at the x variable, the highest exponent on x is 1. So that makes those factors linear. It means you can't have a factor that's like x squared, okay, because that would be a quadratic factor. Now, if you're asked to write the linear factorization, have only that, you're done. Every piece should be totally factored. If it asks you to write the polynomial, then that generally means we want you to multiply that out and get like x cubed, whatever. Any questions on that? Okay, another trip down memory lane, the rational zero test. In Algebra 2, you may have referred to this as the rational root theorem. So those things are the same thing. And I'll give you a moment to jot that stuff down. You guys are doing a great job. The rational zero test is going to come in handy for us when we can't factor a polynomial. So there was a question on the quiz, like write the complete factorization, and then some people did use their division to help, right? They're kind of struggling, how do I factor this cubic polynomial? I don't know how to do it. Okay. In those cases, if I didn't already give you a factor like I did on the quiz, you would then use this method, which is the rational zero test. So rational zero test says f of x has to be a polynomial with integer coefficients. Just remember real quick what integer means. Nice numbers. Numbers like 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4, and also 0. And every rational zero, if a rational zero exists, it will come in the form p over q. Okay. Where p and q have no common factors, so that means you wouldn't see like 6 over 8. It would be reduced to be 3 over 4. Okay. Other than 1. And p is a factor of the constant. Q is a factor of the leading coefficient. Do you remember doing that in Algebra 2 where you would do like, what are all the factors of the constant? What are all the factors of the leading coefficient? And then we put all the constants over the leading coefficient. You make a list of possible rational zeros. And the only thing that I would add to this rational zero test is when you make that list, you put like a plus or minus in front of every fraction. You look so excited about this right now. Okay, he remembers this is one of his favorite parts of Algebra 2. So you never have to worry if the LC or the constant is positive or negative. Like you don't have to worry about signs. You just put a blanket plus or minus. It could be positive or negative. So we're going to get to an example like this here in just a moment. Before we do that, we have a way to work a little bit smarter, not harder. And so in those cases, we will employ Descartes' rule of signs. Did I tell you you're awesome for writing all this down? Because you are. Like any good math theorem, statement, concept, they're going to start with this let statement to give you some information about what we're talking about. Let f of x be a polynomial that has real coefficients, so you can't have any i's in your coefficients for this to work, and a constant term that's not equal to 0. If the constant term were equal to 0, your polynomial, every single term would have an x in them. And then in order to be able to do Descartes, you would have to factor out the x first and then go to the inside polynomial. Okay, so you could do it, and same for the rational 0 test. Okay, factor out that x and then just start over with that new polynomial. Positive zeros. You are going to just look at your polynomial function and count the number of variations. So that means changes in the signs in f of x. So here's my example in blue. F of x equals x to the fourth plus x cubed plus 3x squared minus 1. This very first term is positive, so there's no change to the cubic term. There's no change to the quadratic. How many changes do I have? 1. Okay, so I have 1 change. The number of positive zeros is equal to that value, the number of sign changes, or less than that by an even integer. So an even integer is the integer 2. If you take 1 minus 2, do you get something that makes sense here? Could you have negative 1 positive zeros? No. So you, like the lowest number of positive zeros you could have would be 0 positive zeros. So because we got 1 sign change right there, in my example, my polynomial must have 1 positive 0. Absolutely, without a doubt, there is a positive 0. To do the negative zeros, I am going to go to f of x, but instead of counting the sign changes there again, I've got to do f of negative x. So remember, when you plug in the negative x, you have to think about, when I'm doing negative x to the fourth, raising it to an even number, it's going to end up being positive, and it's going to keep its same sign. So that's still going to be x to the fourth. When I do negative x cubed, that's going to be negative, which will change the sign from positive to negative. The next one is x squared, so that's going to keep its sign, plus 3x squared. And the next one doesn't have x, so it's going to keep its sign. And I'm not showing my substitution there, I'm just going off of the pattern for the x sign. Then I do the same thing. This time I count the number of sign changes in f of negative x. So this is positive to negative, there's 1. Negative to positive, there's 2. And positive to negative, there's 3. So I have 3, or less than that by an even integer, 1, negative 0. This means because this original polynomial was a 4th degree polynomial, that I could have 1 positive and 3 negative. I could have 1 positive and 1 negative, and then the other 2 would have to be imaginary. Okay, so we're not really thinking about positives and negatives there. So that can kind of help you work smarter, not harder. What I would do then in my work is maybe check my negative zeros first, because what if there's 3 of them, then I have a more likely chance of catching one of them. The multiplicity would just be, yeah, like, so if you had a positive solution of 1 that had multiplicity 2, that would count as 2 positive zeros. but you wouldn't be thinking about multiplicity right here. You don't need to consider it. Multiplicity is more for graphing. Okay. Let's do an example finally. Example. When I have this direction, write f of x as a product of linear factors and list all the zeros, it's basically like do all the things. The only thing I'm really not being asked to do here is graphing. Of course, I could graph it after we do everything. Right, f of x is a product of linear factors and list all the zeros. F of x is equal to 2x to the 4th plus 3x cubed minus 8x squared plus 3x. Now, one thing I would always do, like going forward in the chapter, is like stop at every problem. Like you have multiple ways now to solve polynomials, factoring and this like rational zero test. If I could factor, I would factor, because factoring is going to be working smarter, not harder. It's going to get me an answer faster. So I might look at this and see if I can factor. One thing I do notice about this is all the terms have x. So at some point for the rational zero test or Descartes' rule, I'm going to have to factor out that x. I'm just going to do that right away. So I would factor out the x. Put the x out there. One time there. X times the quantity 2x cubed plus 3x squared minus 8x plus 3. And by factoring out an x, I now have found one of my zeros. One of my zeros is 0 because I have a factor of x. And I now have one of my linear factors. I could keep working and see if I could factor the cubic that remains, but that is not going to factor by grouping. So now we need to go into like, what do we do if we can't factor by grouping? Then we got to do this like what I call synthetic guess and check. So you're going to make a list of possible rational zeros. They're not all zeros, but if there are rational zeros, they will appear in this list. And this is where we do that rational zero test. So we've already factored out the x. We found that 0 over there. Let's look at factors of our constant, 1 and 3. Factors of our leading coefficient, 1 and 2. And then these are our p's, factors of a constant. These are our q's, factors of the leading coefficient. We put the factors of the constant over the factors of the leading coefficient. So I would start my list with plus or minus, and then I would do 1 over 1, 3 over 1. That's just 1 and 3. And then to finish the list, I got to take 1 and 3 and put them over 2. Okay, so that would be 1/2 and 3/2. Now, you could go straight into guess and check here. The other option you have is to think about Descartes and consider what are the possible numbers for positive and negative zeros, because then if you find out one of them doesn't happen, like you have 0 positive zeros, then I wouldn't check any of the positive zeros. That would just reduce the amount of work I do. So when I look at this f of x, 2x cubed plus 3x squared minus 8x plus 3, I can ignore the x I've already factored out. How many sign changes do you have right there? 2. So you have 2 or 0 positive zeros. And then when you do the negative f of x, f of negative x, the odds will change signs, the evens will stay the same. So it'll be negative 2x cubed plus 3x squared plus 8x plus 3. And there's only one change there. So if I were choosing, I might start with the negatives. Like it's possible I have 2 positives, but I know for certain I have 1 negative. What if the other 2 are imaginary? Like don't have any positives, and I'll check for positive numbers if I didn't have to. But it's up to you. Let's kind of split the work. So this group, can you check 1? Can you check -1? Can you check 3? Can you check -3? And you guys check 1/2, and you guys check -1/2? Okay. Do a quick synthetic, and let us know if anything works. You're working with this one we factored, the x cubed. 2, 3, -8, 3. Did anybody find one that works? Chris, what's yours? Okay, regular 1/2. Let's hope it works. Add down to get 2. 2 times 1/2 is 1. Add down to get 4. 4 times 1/2 is 2. Add down to get -6. -6 times 1/2 is -3. Oh, yes! Down to 0. So I can add that to my list of zeros. Now, did some other people may have found one that worked? Did anybody else find one that worked? 1. 1 works and -3 works. But what should happen is, like, if Chris found 1/2, or you guys found -3, or you guys found 1, take whatever's left over, because this was x cubed. This is now x squared. And, you know, in interest of time, what if the other two were imaginary? I would just factor, because I can factor or quadratic formula any quadratic. Okay. For me, it would be easiest to factor out the 2 from every term right away. And then I can easily see what are factors of -3 that adds to make 2, positive 3 and -1. So that's 2 times x plus 3, x minus 1. And then I get the solutions, x equals -3 and positive 1, which you guys found through synthetic, right? So you can either keep working synthetic and you can build off of this, but I usually stop when I get to quadratic and solve my quadratic. Paige. It does not produce a 0, so if you, like you said, x plus 3 equal to 0, x minus 1 equal to 0, how do you feel about 2 equals 0? You feel bad, don't you? That is not true, so it does not produce a solution. Okay, so anytime it's a number, you just ignore it, really. It doesn't make any sense. I mean, you might not feel that, but I do. Okay, so you have all 4 zeros, right? What else did that problem ask us to do? Write the linear factorization. So I would say f of x equals, I've got my x that I originally factored out, right? That's my solution 0. I've got my x plus 3 and my x minus 1. I can pull those out from the factors that I had before, okay, or from my zeros. And then here's the issue with 1/2. You could write it as x minus 1/2, but then in order to be the original function and have a leading coefficient of 2, you would need an extra just random factor of 2 out there. So for me, if I pay attention to my LC, I can get a factor or a solution of x of 1/2 by having x minus 1/2, or if you just take your denominator and put it in front of your x. If you set that equals to 0, wouldn't it also give you 1/2? Okay. So that would be my other factor, 2x minus 1. I like that better than having a fraction in there, because like when you factor, you don't find that. You find 2x minus 1. So now you have all the things. Okay? Okay. Any questions that I can answer or clarify? Now, there is a problem that I wanted to do as an example, but we're running tight on time, so I'm just going to give you a quick rundown of what would happen so that I can pass back the quizzes. Sometimes in the homework, instead of like not having any information provided for you, I'm going to provide you with a complex 0. What do you know when I give you this one complex 0? That the conjugate also is a 0. So what you can do in order to find the missing 0, because this has a degree 3, so you're missing some zeros. Write these out as linear factors. Multiply to get a quadratic. And these will always come out to a nice quadratic with real coefficients. You won't have i's anymore. And we did that with like radicals in one of our explorations. And then take your quadratic and use your quadratic as a divisor. So use the quadratic as a divisor. Divide the polynomial, f of x, the cubics, by the quadratic. You're going to get the one linear solution that you don't have. Okay? So you're just doing a little bit of algebra. Okay, so you do have a book assignment, and then I'm going to pass back your quizzes. If you have quiz corrections, you'll also be receiving this little pink sheet that I'm going to have Zach hand out to everybody. Okay, and you're going to mark on that pink sheet as you're working on your corrections, and note that corrections are going to be due on Tuesday of next week.